Okay, so this video is essentially a screencast of the lecture I've given in class, and you can use this to help you with the homework and review as you study for the test. So, significant figures, right, or as affectionately known as sig figs, sometimes significant digits as well. So when you perform a calculation, sometimes the calculator, you press the equals button and you get just a bunch of decimal places, and you're wondering, well, geez, how many of these decimal places, how many of these numbers am I supposed to write down, right? Are you more accurate if you write down all the decimal places that the calculator gives you? Or maybe not all of them, but some of them, and if so, which ones or how many are you supposed to use? How many of these numbers the calculator gives you, you're supposed to use? I should warn you, your calculator knows diddly about significant figures. Okay, so it's up to you to either round up or round down to the correct number of significant figures. Alright, so what is the difference between a number like 15 and 15? Oh, this is 15.00, right? Maybe there really isn't a difference. Well, if you did this, enter these numbers in your calculator and perform some operation, your calculator would give you the exactly same number. Well, that's because it doesn't know anything about sig figs, but there is a difference. For example, 15 is known only to the ones place, but 15.00, we know this is measured to the hundredths place, to the second decimal place, and it turns out to be a 0. So there really is a difference. And you might be wondering what's the difference, or what's the reason for this watch here, this precision timepiece. So we'll be talking about accuracy and precision and what the difference is there. Right, so you've heard of accuracy and precision. They're really not the same things, and we'll have to talk a little bit about that. Alright, so if you do this calculation, 4 miles in 12 minutes, you end up with 0.333333 because 4 is 1/3 of 12. Right? How many of these 3's are we supposed to keep? Right? The answer is given to us by sig figs, and we only keep one of them. Now, maybe that seems surprising to you. You think, well, calculator works so hard to give me all these 3's, and then I only use one of them. But there's a reason for that. Okay? The rule that governs this concept of sig figs is that, and this is only for multiplication and division, which is most of what we'll be doing in class, multiplication and division. The number of significant figures in the answer is the least number of significant figures involved in the calculation. It's kind of a fancy way of saying we round to the lowest number of sig figs. So in 4 here, there's only one number. There's one significant figure. Therefore, and obviously in 12, there's 2 of them. But so in our answer, we only keep 1. All right. Now there's a 0 here, and you're like, well, isn't that significant? Well, we'll find out that actually not. This 3 is the only significant figure there. So, all right. So before we start talking about sig figs, you notice we rounded this number from 0.333333 to just 0.3. So I want to talk a little bit about rounding. All right. Before we talk about rounding numbers, a little bit of decimal review, because I'm not going to test you on this, but I'm going to be referring to these decimal places by their names. So ones, tens, hundreds, thousands, so forth. Tenths, hundredths, thousandths. We already discussed this in the lecture on scientific notation when we discussed the powers of 10, right? So 10 to the 0 is 1, that's the ones place. 10 to the 1 is 10, that's the tens place. 10 to the 2 is 100, and so on. 10 to the minus 1, tenths place. All right. So as I start talking about rounding, I'll be referring to the decimal places by these names here: tenths, hundredths, thousandths, so forth. Okay. So when we round, we look to one decimal beyond the place. Right? So when we round, we look to one decimal place beyond that which we're going to keep. So say we want to round these to the ones place. Here's 5 is in the ones place. We look to the 5. Right? Here 2 is in the ones place. Right? We're rounding to the ones place. We look one decimal place, I guess, to the right. Right? One decimal place beyond. What we'd call it one more degree of precision. One more decimal place. If this number is 5 or more, we round up. If we're rounding to the ones place, we look to one decimal place to the right. If this number is 5 or more, we round up. So we're going to 5 or more round up. Similarly here, if this number is 4 or less, we round down. Okay. So we're rounding to the ones place. So the ones place is the highest degree of precision, or the last number we can keep. So we read it from left to right, 135. This 5 becomes a 6, and it's 136 is our answer. If we're rounding to the ones place here, 2.1234 simply becomes 2. Right. And notice here now, 2 is less than 2.134. Right? We lost the 0.1234 part. So we actually did round down. 2, this number 2, right, is less than 2.1234. So we rounded down. Notice when you round down, you never change this number. The 2 does not become a 1. Right? We do not change that 2 to a 1. It's just we lop off the back half here. So, the other thing to keep in mind is, yes, we round down, but the other thing that we don't do, and you have to be careful of this, okay, all right, 2, sometimes it's tempting to put in a 2.0. Please don't do that, because now what you've done is you're including the tenths place, and we only need the 2. So don't add a 0. All right, again, so in other words, we round to the lowest number of sig figs. What are these sig figs that you talk about? Right? What is a sig fig? How do we know how many there are? Well, there's a set of 6 rules. I'm going to go through each of the, whoops. Can I back up? There we go. There's a set of 6 rules that allow us to determine if a digit is significant or not. Notice I say if a digit in a measurement is significant. These are all going to be, these sig figs are always going to be from a measurement of some sort. And it could be a length measurement that we'll be doing in lab, or it could be a volume measurement or a mass measurement. It could be, I don't know, some other scientific measurements like maybe pH. Could be even time or temperature. All right. And these rules are based on the instrument that's used to make the measurement. Now, and oftentimes you're not going to have the instrument in front of you. Okay. In lab, of course, you would. But in paper and pencil homework, you wouldn't. But the person who took that measurement would have expressed that number to the correct number of sig figs. And then it's up to you when you're doing the calculation to round to the correct sig figs. Remember, the main rule is we always round to the lowest number of sig figs. How do we know what number of sig figs it is? Well, let's look at a little example here. If we wanted to determine the average thickness of a sheet of paper, you know how thin a sheet of paper is, and the only instrument we have is a metric ruler. Now this here is actually a slide ruler on the side here. It's not a metric ruler, but never mind about how to read a slide rule. We have calculators now instead. And the nearest, or the smallest division on this metric ruler is the millimeter, which is 0.1 of a centimeter. So if we look here, here's our metric ruler. Starting at 0 here, 0 to 1, that's 1 centimeter, 1 to 2, 2 centimeters. The little lines in between, those are the millimeters. And we have a whole lecture on the metric system later, but this is to just kind of get you thinking about this. The centimeter is divided into 10 itty-bitty millimeters. So this would be 0, and from here to here, this is 1 centimeter. Each centimeter is divided into 10 equal divisions, and those divisions are called millimeters. So 1 millimeter is 1/10 of a centimeter. And so the smallest thing we can measure with this is a millimeter in thickness. Now sheets of paper are far thinner than that, so how can we possibly use this? Well, what we could do, there we go. If we measured a whole bunch, let's say like 220 pages, right, measure the thickness of not just 1 but 220, right, and then we measure that, it's 2.4. Remember, we measure to the 10th of a centimeter. nearest millimeter, so 2.4 centimeters. This pile of papers is 220 pages and it's 2.4 centimeters. We do the math, we end up with 0.01090909, and actually 0.9 repeating centimeters per page. Okay. So we've actually determined the average thickness of one of those sheets of paper, but we did it using a device that only measures to the nearest tenth of a centimeter. Notice the first number here is actually in the hundredths. Right? Our instrument measures to the nearest tenth, but this is hundredths. Okay, so we got a couple issues here. How can we possibly express this number if we used it with a measurement of a device that only goes to the nearest tenth? And then how many of these do we keep? Right? So that's where these sig figs rules, a set of six rules for determining sig figs, comes into play. Oh, and there's our stack of paper, right? So we measure this. This is 2.4 centimeters, and it's 220 pages, or 220 sheets. And by doing the math, we can calculate the average thickness. All right. So the calculator gives you something like this, but if we can only measure to the tenth of a centimeter, does it make any sense to include all of this? Actually, it doesn't. So we're going to apply these rules of sig figs. First rule, all non-zero numbers 1 through 9 are significant. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. If it's something other than 0, it's significant. So this number has 6 SF, 6 sig figs. Right? 1, 2, 3, and then 4, 5, and 6. Right? What this means is the other the other 4 rules, the next 4 rules are all going to be dealing with zeros. Because if we've taken care of all the non-zero numbers, then what about zeros? Might not have known this before, but it turns out there are 3 kinds of zeros. First one we'll talk about are sandwich zeros. These are zeros between non-zero numbers. Right? So these highlighted zeros here. So if 2 is significant according to rule 1, this second 2 is significant according to rule 1, then anything between that also has to be significant. So sandwich zeros, these guys are always significant. Now we've got another kind of zero, leading zeros. Leading zeros come before the first non-zero number. I'll put it over here. We read left to right, so these come before the first non-zero number. This is the first non-zero number. So these guys, they're never significant. This number 304.1, what are you doing with these zeros out here? Why would you ever include those? They don't make any sense. We started counting back here at 0.1, right? We got 0.1, 0.2, 0.3, 0.4, up to 0.9, and then 1, and then maybe 3.8, 3.8, 3.9, 4, 4.0, and then 4.1. So we started counting back here. It doesn't make any sense to include numbers to the left. Similarly, these numbers here, likewise not significant. We didn't start counting here at the ones. We started counting way back here at what would be the 10,000th place. So 0.0001, 0.0002, 0.0003, 0.0004, and so forth. In words, it would be 1,234 10,000ths, but we'll just say 0.1234. Okay? So clearly, non-zero numbers are significant, but these leading zeros are not. That also includes, what if we had something like this? What if it was 0.000001? How many sig figs is that? Well, all these zeros are leading. We've only got 1 sig fig. Okay. The next type, we've got 3 types. Sandwich zeros, leading zeros, and now trailing zeros. Trailing zeros are those that come after the last non-zero number. Again, we read from left to right, so when I say come after, they're to the right. Come after the last non-zero number. And it turns out that if you wish, there's two flavors. Some books will put both of the trailing zeros in under one rule. I'm going to split it up into two. Trailing zeros without a decimal are not significant. And what I mean by decimal point, we're talking about that little dot. So you notice 100, and there's a dot there now, it's gone. Right? If the dot is there, it's different. If the dot is not, that decimal point isn't there, trailing zeros are not significant. Right, so I'm going to just draw a little arrow. No decimal point. So those trailing zeros are not significant. So this has just one sig fig. Similarly here, no decimal point. So those trailing zeros are not significant, so then we have just two sig figs. Trailing zeros with the decimal point. So first it was without, and now it is with the decimal point. These guys are significant. Actually, let me clean this up a little bit. Get that off of here so we can see what's going on. All right, notice the decimal point in green. Okay, if we include the decimal point, then these guys are significant. So I'll just highlight that with another arrow. All right, if you include the decimal point, then trailing zeros are significant. What about this guy? Well, here these are leading zeros. They come before the first non-zero number. So these guys are leading. They're never significant. Right. Then we've got a sandwich zero and a trailing zero. Now, trailing zeros, if we don't have a decimal point, they're not significant, right? Rule 4. But here, clearly, there's a decimal point, right? It's 0.00020. So we've got this trailing zero in a decimal fraction, right? So this guy is significant. So the 2040, these three guys here, I'm sorry, these four guys, these four digits here are significant. So we have 4 sig figs. All right, so that's rules 1 through 5. First rule deals with non-zero numbers. The next three, the three types of zeros. The last one, the last rule here, talks about what we call counting numbers or exact numbers. Kind of a little bit of a different concept here. All right, counting numbers are known to what we would refer to as an infinite degree of precision. Right? They're really not measured, they're just counted. So for example, a dozen eggs, what a dozen is exactly 12, right? 12.00000 out on into infinity. It's 12 exactly. It's not 12.1, you can't have 0.1 egg. It's not, 11.9, it's exactly 12. Similar here in our example, we counted 220 pages, so it's 220 exactly. Right? So if we look up here in this calculation, we had this first number here has 2 sig figs. Right? According to rule number 1. Rule number 6 tells us that we don't even need to consider this. I mean, there is no decimal point. Here's a point, now it's gone. Here's a point. But that doesn't matter if there's a decimal point here or not, because this is an exact number. And with exact numbers, you do not need to consider how many sig figs are there, because they're always going to be known to a higher degree of precision, an infinite degree of precision. So 2 sig figs, our answer must have 2 sig figs. Let me back up. Wait a second. Did I do the math? Where did I do the math? All right, so we're going to round this to what now? Thought I did the math here. Okay. We need 2 sig figs. In any event, we've got what? We have 2 sig figs in our answer, or in our calculation. Our answer must then just have 2 sig figs. Remember, leading zeros do not count. So there's our first sig fig, the 1. This 0 is also significant, so what are we going to do? We're going to round up. This 9 tells us we round this 0 up to a 1. So 0.011 centimeters per page. Alright, so some more examples here. Again, rule number 1, non-zero numbers always significant, so there's 6 here. Here we've got a couple sandwich zeros. These are also significant, so there's 7 sig figs. I'm going to go through this pretty quickly, but you can, as you're viewing this, if you want to, you can always pause it and make sure that, go ahead and count all of these and make sure that I did this correctly. Rule number 3, leading zeros, never significant, so 23 is just 2. 0.00004, none of these are significant, it's just the 4, so there's 1 sig fig. Trailing zeros, kind of depends. If there's no decimal place, it's not. So 334, right, has 3 sig figs. 3,000, right, just has 1. Now, think about this. Let's say for 3,000, let's say we had a measuring device that the smallest division was, say, 100. So we want to keep the hundreds place, but we don't want to keep the tens or the ones. Okay, so what I'm saying here is we want to measure to the hundreds place, but we don't want these other zeros, the tens and the ones. How could we possibly express this number then? Well, the first lecture we had was on sig figs. So I'm going to put 3,000 here. Right. There's just 1 sig fig. But if I write it as 3.0 times 10 to the third, now how many sig figs? Well, clearly there's a decimal point. This is a comma, not a decimal point. Here we've got the decimal point. So 3.0. This is now a trailing 0 with a decimal. This is significant. So there's 2 sig figs. So if we express this number to the hundreds place, we can also do it maybe to the tens place. 3.00 times 10 to the third. This has now got 3 sig figs. Right? This third 0 we can just omit, right? So your calculator doesn't know anything about sig figs, but you're expected to, and you can express any number to the correct number of sig figs, even if it's something goofy like this, but you might have to resort to scientific notation. Right? As I was mentioning earlier, if we have a decimal point, then trailing zeros are significant, so these guys are significant, so there's 4. Here, none of these leading zeros count. The 2 obviously counts, and this trailing 0 counts, so there's 2, 3, and likewise this 3,000, only 1, but 3,000 decimal point, now there's 4. Okay. Exact numbers, don't need to worry about it. I'll just say do not consider exact numbers when determining sig figs. Right up, sig figs. Okay. Alright, so, here's the math. So, when we round this off to sig figs, this is incorrect. This should be rounded to, what did I say, right? We're going to round to 2 sig figs, so this becomes 0.011 centimeters per page. Alright. One more thing to keep in mind, I think I might have mentioned this. No, I didn't mention it, but I did kind of use it. When you're determining sig figs in scientific notation, you only worry about the coefficient. The times 10 part is just placeholders. You do not worry about the times 10 part. It's only the coefficient. Alright. So let's do a little practice here. Round these guys off to the correct sig figs. All right. So the first thing we have to do is determine how many sig figs. We've got some trailing zeros here. They're significant, so there's how many? 1, 2, 3, 4. So I'll just put the number of sig figs above each one here. What about in 0.0042? These are leading zeros, they never count, so we only have 2. I'll underline the significant ones. So how many should our answer have? Always use the least number. The least number is 2, so our answer has 2 sig figs, 0.013. 2 sig figs. Let's try another one. 5,000 divided by 12.200. You don't see a decimal here. So we've got 3 trailing zeros, but none of them are significant. We only have one here. 1 sig fig. 12.200. These trailing zeros also count, so we've got 5 sig figs. How many does our answer have? Always the least number. So what? 400. Right? We only have 1 sig fig here, and that's the 4. Be careful, don't put a decimal there. Certainly don't put a decimal point and a 0. Right? It's just 400, no decimal point. We have some numbers in scientific notation. Again, remember, we only look at the coefficient. So 9 and 3 are significant. What about the 0? Yeah, it's a trailing 0, so it's going to be significant. We've got the decimal point there, so it's significant. So we've got 3 here. What about this? Here we've got a leading 0. That doesn't count, but the 2, and again another trailing 0 with the decimal. So we've got 2 here. So our answer must have just 2 sig figs. Look at our, right, we round this off to 1.9. Again, don't worry about the times 10 part. Do notice, however, when we talked about scientific notation, -3 and -7, when you multiply, you add the exponents. So -3 plus the 7 is +4, and we end up with 2 sig figs. 1, 2. Okay. We have a division now. 1.67 divided by 4.00. We've got 3 sig figs here because it's easy enough, no zeros. Again, we've got a decimal point and a couple of trailing zeros. So there's 3 here, so our answer must have 3. See if I did this right. 4.18, we'll round this to 4.18. And again, remember, when you divide in scientific notation, you subtract the exponent, so it's 23 divided by 12. 23 minus 12, which would give us what? 11. Well, why doesn't this exponent here equal 11? Well, that's because 1.67 divided by 4 is actually what? 0.418. That's not in proper scientific notation. This would be 0.418 times 10 to the 11th. So what we do is we have to make this number larger, move that decimal point over, so we have just one number to the left of the decimal, so it's 4.18. The coefficient got larger by a power of 10, so the exponent has to get smaller, so it goes from 11 down to 10. All right. So we got multiplication and division nailed as far as determining sig figs and calculating. What about addition and subtraction? Are they the same way? No. Completely different concept here, just to make life interesting for you. Addition and subtraction use the concept of precision. Remember, we talked a little bit about precision ahead of time with basically I said precision is another way of thinking of decimal places. Okay, so 2 ways to think about it. You can think about it as reproducibility in a measurement, or you can think about it as the number of decimal places in a measurement. Kind of 2 different ways of thinking about it, but they actually are related. So how are these 2 ideas related? Well, let's take a look first here. Accuracy, and I don't have it here, accuracy is a way of expressing how close you are to the correct or accepted value. This is determined by percent error. We'll get into this more when we get into the laboratory, so I'm not going to go through the details here. But there is a formula for determining the percent error. Notice in percent error, you have to know the correct value, right? In order, if you're accurate or not, you have to know what the correct value is. Sometimes in science, we're doing original research, we don't know what the correct value is. So how do we know if we're doing it right? Well, this is where precision comes into play. So precision is a measure of how reproducible our data is, and it's measured by calculating the percent difference. Right? So we don't, instead of using the correct value, CORR here is correct value, we're going to use an average value of a number of different determinations. So again, we'll talk more about using this in the lab, and we'll actually do these calculations, each of these calculations in a couple different labs. Right. One way of thinking about precision is reproducibility. So we have this dartboard analogy. Right. Back up a second. How reproducible they are. Percent difference essentially is how different the data is from one data point to the next. So if we look here now, the target, the bullseye is here, and we're throwing 3 darts, and they're kind of all over the place. They're not on target, and they're not clustered together very well either, so it's neither accurate nor precise. Here they're all clustered together, so it's pretty precise. We get the same answer pretty much every time we throw the dart. It lands in the same place, right? So it's reproducible, but we're off target, so we're not accurate. Down here, this is what you really want, where you're accurate, right on target, and precise. They're all clustered together. This example here is kind of dangerous. And the reason I say it's dangerous is because if you look at the average of these guys, right, we take the average of these two, it's right in the middle. We take the average of these two, it's right in the middle. So if we took the average of those 4 determinations, you'd think, oh, well, we're right on target. But the problem is there's not a lot of precision here. We don't know where that next dart is. We don't know where that next data point is going to be. Maybe it's way off here to the side, and that's going to skew everything off. So what we need to do is kind of think about both accuracy and precision. If you're precise but off target, that's not necessarily bad, because there might be something you can do to bring these data points back onto the target, right? Back onto the correct value. But if they're all over the place, there's nothing you can do. You don't know if do I need to shift my, if I'm throwing the darts, maybe I need to stand over to the right more, but that's going to throw these guys off. Maybe I need to aim a little bit lower, but that's going to throw these guys off. So there's nothing you can do with a data set like this to bring it into being accurate. But if the data is clustered together nicely, then you can. So this isn't really the worst case. All right. Another analogy here, just because everybody likes kittens. So we're going to throw these mittens at the kitten. He's going to try to catch him, or maybe it's a she, I don't know. And nailed this kitten with the mitten right on target, right? Here, these guys, again, they're clustered together, so it's good precision, but they're off target, right? They're not accurate. Here, we nailed his little paw, so we're accurate. And I don't know, maybe there's 4 of these piled up, but she can't tell. So let's assume this is precise as well. There are 4 of them all clustered together. Here, right, this is that one example I said is dangerous. You think it's accurate because, again, if you took the average of these guys, right, you find out you're right on target. But that next mitten, I don't know, I can't really draw a mitten very well, but let's say maybe that next mitten's way up here. Okay, that's going to throw all the data off. So this really isn't accurate. The average might be accurate, but it's kind of misleading. All right. So as I mentioned before, we can think of precision as degree of reproducibility, but you can also simply think of it as a number of decimal places. So this value 2.1 has 1 degree of precision. It's 1 decimal place. 2.12, 2 decimal places. 0.123, 3 decimal places, 3 degrees of precision, and so on. Okay. So the question is, right, how is the number of decimal places related to reproducibility? So say you're working in a factory or a lumber yard or something, and your boss says, all right, I want you to cut some boards, and I want them all 1 meter in length, and get it done before lunch. Okay. Now notice he said 1 meter. He didn't say 1.0 or 1.00 meters. Doesn't matter. Is that the same thing? Well, let's say you've got this meter stick. And again, let's just review the metric system a little bit. This is a meter stick which would actually go up to 100. This is 90. This would be 91, 92, 93, 94, 95, 96, 97, 98. 99 is here, and then 100. So in a meter stick, there are 100 centimeters. Centi means 100, just as there's 100 cents in a dollar, 100 centuries in a year. So this would be 86, 87, 88, 89, 90. Right? Those would be 90 centimeters. and the little divisions in between are millimeters. Right? So again, a millimeter is 1/10 of a centimeter. Okay, so if we had something that was, say, I'll put it over here, say between 7 and 8, like that, this would be 97. This is halfway between this little longer tick here is 97.5. This would be 97.6 centimeters. Okay. All right. So we've got this meter stick, and we're going to cut these boards. So we cut the first one right off at 1 meter. Okay. 1 meter, 1.00 meters. Good. Is it the same thing? Not quite. We'll talk about that. Now this guy, we cut him a bit short. Did we? Well, if you look at his point, this would be 80, 88, 89, I'm going to say 89.5 meters. But if your boss said 1 meter, he's saying measure to the nearest meter. If we round to the ones place, this arrow is supposed to be pointing at the 0. Here's the ones place. This would be rounded off to 1 meter. Right? We cut the next board. It's a little bit longer. What's its length? 0.955. So here's be 90 or 0.9 meters, 0.91, 0.92, 0.93, 0.94, 0.95. Halfway between 5 and 6. That looks like another 5, but it's a 6. Right. So this would be 0.955 meters. Again, if we round to the nearest meter, to the ones place, this would be 1 meter. Cut a fourth board. Ooh, it's quite a bit longer. If I stuck another meter stick out here, maybe I could measure this guy. It's 1.135 meters. Here we're rounding down. Again, we measure to the ones place. We look 1 degree of precision, 1 decimal place beyond it. If this number is less than 5, so 4 or less, we round down. So 1.135 is also going to equal 1 meter when we measure to the nearest meter. So show up at your boss's door with all these boards, all different lengths. How reproducible are these? Well, they're kind of all over the place, you know. And your boss is asking, what the heck did you do? Maybe your boss should have said 1 meter. Well, didn't he say 1 meter? No, he said 1 meter. Maybe he should have said 1.0 meters or 1.00 meters and given you what we refer to as precision, some idea of the precision or the tolerance in these numbers. So a measurement, it really has 3 parts. It's got the value. Right? It's got the unit with the thing that we're measuring, in this case meters, but it could have been grams, could have been milliliters, you know, some volume. It could have been pressure, air pressure, say in atmospheres or something like that. And it also has the precision, how many decimal places. So here we've got the value as 1. The precision, well, this is off. This arrow should be pointing to the 0. We know this, to the 10th place. And of course the unit, what it is that we're measuring. Alright, so if you think about it, both ways of thinking of precision are correct. For us, though, however, simply the number of decimal places is probably going to be most useful. Right. So we got this idea of precision. Now we can deal with addition and subtraction. Remember, for multiplication and division, we deal with sig figs. Here, we deal with precision. We deal with the number of decimal places. So the rule here for addition and subtraction, for adding and subtracting, it's similar, but we always, the answer is always going to have the fewer number of decimal places, or if you wish, degrees of precision. Alright, so you enter these two numbers, you add them up, easy enough. You get 47.23, make sure you include the unit, the meters. Is this correct? Actually not. when you do this in your calculator, you're assuming there's a 0 here. But we don't see a 0 there. What is this number in the hundredths place? Is it a 0? You're kind of assuming it is, but you don't know. We don't really know what is here. So we're adding something we don't know to 3. Well, if we don't know what we're adding, the only thing we can say is, well, it's at least 3, but it could be more. We really don't know what this number is. Right? We really don't know. So if we don't know what the number is, does it make any sense to include it in our answer? You can't just make up numbers and pretend you know stuff you don't. So we're going to have to round this number down to 47.2 meters. Right? This first number here, 23.0, it's 1 degree of precision, 1 decimal place. Second one is 2 degrees of precision, 2 decimal places. Our answer can only have 1 decimal place, 1 degree of precision. Similarly here for subtraction, when we do the subtraction, we're subtracting 3 from what? Well, 3 from 0. We're going to have to borrow the 1 and whatnot, and you can do that. But we're assuming there's a 0 here. But it actually wasn't included in the measurement. We don't know what this is. So it doesn't make sense, and it's not fair to say that we know it's a 7 when we really don't. So what have we got here? We've got 2 degrees of precision for the first number. We have 3 degrees in the second number. 3 degrees of precision. Precision. You don't need. All right, if I use the degree symbol, clearly I don't need to write the number, the word down. Okay. I'm gonna fix that. I don't like that at all. Okay. So the first number we have 2 degrees of precision. In the second number we have 3 decimal places, 3 degrees of precision. So how many in our answer? The least number? We should only have 2 degrees in our answer. So we do know to the hundredths place, right? That was measured. In the first number it's 5, in the second number it's 4. So we do know what this is. So what are we going to do? We're going to look to 1 degree of precision beyond the number we're going to keep. The 7 tells us we're going to round up. So it becomes 51.21. And the unit is grams. All right, so this should take care of everything you need to know about precision, accuracy, and sig figs. Just be careful when you're adding and subtracting. It's a different set of rules. We're looking at the number of decimal places. It's precision. Right? When we're multiplying, dividing, we have those 6 sig fig rules. So for example, 23 up here, 23.0 meters. Yeah, it only has 1 degree of precision, but it has 3 sig figs. That would come into play if we had to multiply this by, or divide 23 by something. Okay? So multiplication and division, we got sig figs. For adding and subtracting, it's the number of decimal places.